Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to describe how work can change the potential energy of a system and to introduce what I'll call a more generalized theorem of work and energy. So in my previous video I talked about how work can affect the kinetic energy of a system, how the work done on a system is equal to the change in kinetic energy of a system, and that's what's generally called the work energy theorem. In this video, we're going to take a look at how work can change the potential energy of a system. So here we have my star of a lot of my videos here, young Timmy. And Timmy has this basketball. And we're going to consider the system of the basketball and the earth. All right, so Timmy's really not important for this discussion at all. We know that that basketball has a certain potential energy that we could describe by the equation mgh, where I'm going to go ahead and measure h from a datum on the ground. At this location, the ball would have a positive potential energy because it's up above the datum a distance h. It's important to think about, well, how did the ball get there? In some way, shape, or form, that ball had to be carried up to this position. So imagine that the ball starts here, what I'm going to call position 1. And imagine that somehow the ball gets moved up to position 2, like maybe somebody's on a ladder carrying the ball up here to Timmy. So the force required to move that ball from 1 to 2, that would be an upward force. And that force would have to be supplied by some external agent, some person maybe carrying the ball. There's also a gravitational force acting on the ball, which would be down, equal to mg. Now, as long as this ball is carried upward at a relatively constant speed, then the net force on it's 0 pretty much the entire time, which means these two forces are equal. The work done by the force applied to the ball is going to equal this force times the distance that I'm going to call h, and that's some positive value. Now, if the ball is moving at a constant velocity, then these two forces are equal. So the work done on the ball would equal the term mgh. Now you'll notice that that's equal to the change in potential energy of the system, because the potential energy at this location is 0. The potential energy at this location is mgh. So the change in potential energy would be the final potential energy minus the initial potential energy, which is this term. So you'll notice that the work done by this external force is equal to the change in potential energy of the system. Now remember from my previous video that the work done was equal to the change in kinetic energy in that example. So work can change either your kinetic energy or your potential energy. It can also change them both at the same time. So what we're going to do here is I'm going to modify that theorem of work and energy to include potential energies. The net work done on a system by external forces is equal to your change in potential energy plus your change in kinetic energy. This is what I would call a more generalized theorem of work and energy to take into account potential energy terms. The change in potential energy can be written PE final minus PE initial. Remember, change in anything can be written final minus initial. The change in kinetic energy can be written KE final minus KE initial. And this is the most common generic form of the work energy theorem. Usually when you see it written in the book, these terms here and here are on the left-hand side. So you got PE initial plus KE initial plus net work done is equal to PE final plus KE final. Now, whether these are initials with an I or initials with an O, that doesn't really matter. And usually when I write this equation in most of my courses, rather than saying initial and final, I like to attach numbers to the states. So like for in this example, if this were state 1, this I would call state 2. And I would typically write this equation like this. PE1 plus KE1 plus net work done on the system is equal to PE2 plus KE2. This equation seems like kind of a long equation, but I assure you it is one of the most simple concepts in physics, really. This is just saying that energy follows basic conservation laws. This sum represents the total mechanical energy of some system at state 1. The work is how the energy can be changed. That's what work is. It's a transfer of energy by applying a force that's acted on over some distance. And then this sum represents my new total. It really is a very, very simple type of equation. I'd like to go through a quick alternative type of equation that demonstrates really how simple this is. Imagine this building here. And at any given time, maybe let's say 12 o'clock, there's a certain number of people in that room or in that building. And I'm going to call that N1, where N1 is the number of people in the building at some time. Doesn't matter when. Maybe 3 hours go by. Some people are going to go in the door. Some people are going to come out. So now what we're going to have is a delta n, a change in the number of people. I would call delta n positive when people are coming into the building. Delta n is negative when people are going out of the building. If 7 people go in and 3 people go out, your delta n would be plus 4. If 3 people go in and 7 people come out, your delta n would be minus 4. In any case, if I take my original number of people and I add my change, I'm going to get some new number. This is basically what the work energy theorem says. Now the work energy theorem has more detail to it. Well, let's take this and break it down even further. This N1 is the sum of two things. It's the number of males in the room plus the number of females in the room. I said room, I meant building. So I could, if I wanted to, express that something like, let's say, number of males, state 1, plus number of females, state 1, plus the change in the number of people going in and out the door. That would equal my new total number, which if I wanted to, I could break down into detail. Number of males at my new state plus number of females in my new state. You'll notice that this equation has this pretty much exact form. That's all the work energy theorem is saying. My total energy at any given state, which is the sum of two things, my potential plus kinetic, plus any work done on the system as I go from state 1 to state 2 equals my new energy state. So I hope that this video helps describe the work energy theorem. I'm going to make many, many more on using it to solve problems. Have a great day.